Hey everybody, greetings. So in this video we're going to discuss about a very interesting application of singular value decomposition on video processing. Okay, so I have a previous video uploaded. I'm going to put it in the description where I discuss about images and I discuss about the singular value decomposition in general and how it can be used to compress an image, because we are going to use pretty much the same application here. So let's review the basics. Of course, you need to be somewhat familiar with images, but let me remind everybody. In a computer, in any programming language, we are going to represent an image as a classic matrix. Okay, so the size of the image is, of course, the size of the corresponding matrix. And each element in the matrix represents a specific pixel. Okay. If the image is grayscale, it is represented by a single matrix. If the image is colored, so it has RGB RGB scale, I'm sorry, it is represented by three matrices. One matrix is the red intensity, one is the green intensity, and one is the blue intensity. Okay. So each pixel in these matrices represents the value, each element, I'm sorry, in these matrices represents the value of the pixel. Okay. So in a grayscale image, a pixel with a value of 0 is black, a pixel with a value of 255 is white, and all the intermediate integer values represent the shades of the gray. Okay. And the same holds for the RGB. For example, in a specific matrix, let's say that one element has the value of 255 in the red matrix, 100 in the green matrix, and 0 in the blue matrix, and their combination will give us this specific pixel color. Okay. So simple as that. So this image, for example, which is colored, is represented in the computer by these three matrices, and each matrix has integer values between 0 and 255. Okay. So just the basics for the image. Okay. Now, what do we have about matrices? Okay, we need to know some very basic information. If you're a first-year student, you're going to learn about this throughout a basic course of linear algebra. So you need to be familiar with the rank of the matrix, which is the number of its pivots. Of course, the transpose of a matrix, its eigenvalues, or as how some people call them, eigenvalues, the eigenvectors, and of course the singular values, which is actually the eigenvalues of this product right here, and the Euclidean norm, just in case you want to do some comparison at the end. Now, in the previous video, I talked about the singular value decomposition. I would advise you read any basic book on linear algebra. For example, the classic textbook by Gilbert Strang explains SVD. Now, what is an SVD? Let me show you through a graph. The singular value decomposition is a process, an algorithm, where we break down an image into the product of three matrices, U, sigma, and V. Okay. And the special thing is that this sigma matrix in the middle, it is a diagonal matrix, and it contains the elements that are called singular values for this matrix. Okay. And the singular values are placed in this diagonal matrix in order of importance. So simply put, the first elements that you see right here are the most important ones. And as we go down, the last elements are less and less and less important. Actually, they might be equal to 0. Okay. And by important, I mean that if we're going to do some sort of compression where we want to keep only the most brutal, or if you want to note this, the most major information in this matrix alpha, what we can do is we can discard the last singular values of sigma. Now, how many we are going to discuss has to do with the discard, has to do with the application, of course. But let's say we only keep out of these R values, we only keep kappa values, and we discard the rest. Of course, we have to discard the last columns of this matrix here and the last rows of this matrix right here. And in this way, we can get an approximation of alpha. Of course, the more values that we keep, the more singular values we keep, the approximation is going to be better. If on the other hand, we are going to discard almost all of the singular values and keep only a couple, this approximation is going to be very, very, very rough. And you can do this with this application, many things in image processing. Now, I'm going to show you a very interesting application in video processing here. So, as you can understand, what is a video? A video is nothing else other than a collection of matrices, a collection of frames, okay? So any video is actually comprised of thousands of images that are played at a specific speed, okay? And using singular value, we can do something amazing. See this video right here, for example. I have taken it from Matlab. Okay, it's just someone playing this xylophone. Alright, nice. I can do with singular value decomposition a background extraction in this video. What do I mean? I can take this collection of frames from this video where you see this hand moving around, and what I can do is I can extract only the background from this video, which is a static image. So how do I do that? The technique actually is amazing. Let's see it. So this is the outline of the technique. It uses singular value decomposition, and the thing is that this code is just a few lines in Matlab. So it's amazing. Even if you are a first-year student, you can actually perform this with a very few lines of code. So let's say I have my video right here. It's n by n, and it consists of like not even 100. It can be thousands of frames, right? So what do? I take from these thousands of frames that comprise the video, I take only a couple. Let's say I take 1 frame every second, or let's say I take 10 frames every second. So if the video is like 10 seconds long, I'm gonna end up with 100 frames. Okay. So let's say I have this collection of frames that I have gathered from sampling all the video. All right. So what do? I take each individual frame and I sort all of these pixels into a single row. So as you see, this whole image right here, which is a single frame, is reshaped into a single row as you see right here. So I take all of these pixels in this image and I rearrange them in a very long row, right? I do the same thing with the second frame, with the third frame, and so on and so on, and then I'll do it with the final frame. So I'm gonna take all of these rows, which are the reshaped frames, and I'm gonna stack them together. So let's say I have n frames, so I'm gonna have n rows in this matrix. And of course, each image is m by n, so I'm gonna have m times n columns. So this is going to be a huge rectangular matrix. Let's say I'm having 100 frames, so I'm gonna have 100 rows, but I'm gonna have thousands if the video is big. I'm gonna have a very long number of columns. Okay, so a very big rectangular matrix. Okay, so let's call this matrix zeta. So then here's what I'm doing. I'm doing a singular value decomposition of rank 1. So I'm going to do an SVD on this matrix zeta, and then I'm going to discard all of the singular values except the first one, which is the most important one. Okay, so I'm going to do an extremely heavy compression of the matrix zeta. By keeping only one singular value, the compression is extremely high, right? Nice. And then after I do this compression on this matrix zeta, I'm going to extract any row from this matrix. Doesn't matter, all of these rows are going to be the same. So let's say I'm simply taking the first row of this compressed matrix, and then I'm simply reshaping this row, which is very long, into the original image size. And doing that, I can actually obtain the background of the video. So what's the idea here? The idea is to take a lot of frames from the video. Each frame is slightly different from the other, as you see right here. Reshape them into a single row and stack them all together. Now, this very big rectangular matrix pretty much carries a lot of information about the video. So what happens here? If I take this very big matrix and I compress it to a very high extent, well, if I compress it, I'm discarding a lot of redundant information. So the fewest information that I'm going to keep is going to be the most basic minimum information about this video. And actually, this most basic information about the video consists about all the information from the background frame. Okay, so all this hand that you see moving around, since this only appears in just a couple of frames and it moves around a lot, when stacking them together, this will be considered like sort of a redundant information. So when doing a rank 1 compression, this will be discarded, and only the static parts of the video are going to remain. And from this from this collection of frames, indeed, this is the result after I do this SVD compression on the stacked matrix, right? Amazing. I managed to discard this moving hand and only obtain an image that has the background information from the video. And you can do many stuff with this application. This is just an example. But for me, the most important thing is that you can do this with very few lines of code in Matlab. Okay. So in the video description, I'm going to put a link in the paper where we discuss this application. You should definitely take a look at the references in that paper because there are other people presenting this work for different applications and different videos. And I'm also going to put some link in Matlab so you can download the code and perform this application yourself. Okay, so any questions that you have, just write them down in the comments and I will reply to all of them. Thank you very much.